So last day we started off the compiler correctness example. And in particular, we defined the basic definitions which we need for the compiler, and we formulated what it means for the compiler to actually be correct. So what we're going to do today is the final lecture on the course, and we're going to be doing three things. So first of all, as we often do, we're going to start with a quick refresher on what we did last day in terms of the compiler correctness example. Then we're going to move over to think about how to actually do the proof that the compiler is correct, and we'll do a straightforward inductive proof first of all. And what we'll find is that there's a number of issues with this proof that maybe we're not too satisfied with. And what we'll see in the later part of today's class is how we can simplify this proof by using some of the techniques which we've learned about in the last couple of classes, and this will resolve the issues with a simple inductive proof. So we'll kick things off today by reviewing the basic setup for compiler correctness, which we introduced in the last class. So what we introduced there is three function definitions and then the compiler correctness theorem in the red box at the bottom. So we'll review each of these one at a time. So first of all, we defined an evaluation function which gives a semantics for expressions. And this was very simple. The function simply takes an expression as input, and then it's going to evaluate it to give its underlying integer value. So the semantics of expressions is simply given by evaluating them and getting the underlying integer value which it represents. Then secondly, we define the actual compilation function, and what the compiler does is it takes an expression as input and then it translates it down into equivalent code for a simple stack-based machine. And our simple stack-based machine had code which was simply a sequence of push and add operations on the stack. So that's the compiler, takes an expression as input and translates it down to equivalent code for a simple stack-based machine. And then finally, we had the execution function, exec, which gives a semantics for code. So what this does is it takes code as input, and then it takes an initial stack, which the code is going to execute using, and then it will execute all of that code using that initial stack, and it will give you back a final stack. So if you wanted to be fancy, the way you could think about this is that the execute function is taking code as an input, and then it's giving it a semantics as a stack transformer. So it takes a stack as an input and gives you a stack as an output. So that's the basic three functions which we defined in the last class. And then what we have in the red box at the bottom is the equational specification for what it means for the compiler to be correct. And this equational specification actually relates in a precise way the three functions which we've defined above. So it's very straightforward to understand how this specification is actually working. So what we're doing is we're taking an expression E, and then we're compiling it, and that will give us some code, and then we're executing that code using an initial stack S, and that will give us a final stack. And what the specification here says is that the stack which you get from executing things on the left-hand side here should be exactly the same as the original stack, but with the value of the expression sitting on top of the stack. Okay, so let me just get rid of the yellow here and let's go over this one more time. The equational specification says if you compile an expression and then execute the resulting code using an initial stack, you will get the same stack back, but with the value of the expression sitting on top of the stack. So the name of the game in today's class is we want to prove that this equation is actually true for an arbitrary expression E. So, of course, the proof is going to proceed by induction on the expression E. So, as usual, we're going to start off with the base case. So, the base case is when the expression E is simply a value n, or an integer value n. So all we're going to do then is we're going to take this equation here and we're going to plug in the expression E being the value n, and then we want to check that this equation in the red box is actually true. And as usual, we can think, well, where do we start? And one of the pieces of advice is, as always, maybe start with the most complicated expression. So what we're going to do is take this expression in yellow here and plug in e to be val of n, and then hopefully in a few calculational steps, we'll find that we get the yellow on the right-hand side here. So let's see how this actually works out in practice. So on the left-hand side, we had executing the result of compiling the expression, and in this case the expression is just the value n, and then we have an initial stack, and then we want to see that this is going to be the same thing as the right hand side of our compiler correctness theorem. So what are we going to do? Well, it's very easy to see what to do in this case. We can simply apply the definition of the compiler, so we know how to compile a value. So if you look back to the definition of the compiler, what we're going to get is we copy down the execute. The result of compiling a value is we simply have a push operation sitting in a list on its own, and then we copy down the stack here. Okay, so very straightforward first step. We're just applying the definition of the compiler. And the second step is also going to be very straightforward because we can apply the definition of the execute function. The execute function looks at the first operation in the code. In this case, there's only one operation. It's a push, and then it does the appropriate action depending on what it finds. So in this case, if you apply the definition of the execute function, it's simply going to put that value n on to the top of the stack. So we get down to n colon s. And at this point, we seem to be a bit stuck because we can't apply any more definitions, and we don't know anything about the stack s, so we can't do anything with that. So we can apply one of our other tricks at this point. We can try working backwards. So what we're trying to reach here is eval of e colon s, where e happens to be the value n. So if I was to work backwards at this point, what I could write is, what I'm aiming for here is eval of val of n sitting on the stack s. That's what I'd like to get to. And getting from here to here is entirely straightforward if we wanted to work backwards, because if I evaluate the value n, I'm going to get exactly this. So if I was going in the reverse direction, I would be applying the definition of eval. So if I was to write a hint in here, I would say if you unapply the definition of eval, then you're going to get the right result. So this basically completes the proof of the base case. All we had to do is apply the definition of the comp function, apply the definition of the execute function, and then unapply the definition of the eval function, and we have completed the simple equational proof for the base case. So now we can move on to the inductive case. And of course, what we need to do in this case is show that the compiler correctness theorem is true when the expression e is an addition. So it's going to be the addition of two sub-expressions x and y. So concretely, what we need to show is that this expression here is the same as this expression here when e is the addition of x and y. And of course, we're going to proceed in the same way as the base case. We're going to start with the more complicated left-hand side and try and show that it's equal to the right-hand side. So I'm actually going to need quite a lot of space on the slide here. So let me get rid of this header so we can just have the calculation itself on the slide. So what we'll do is we'll start off with the left-hand side, which was the result of executing the compilation of add and of x and y in the context of the given stack s. So then we think, well, what can we do here? So the first thing we can do is we can apply the definition of the compilation function. We know how to compile an addition. So if we compile an addition, what we're going to get is we copy down the exec, first of all. When we compile the addition, all we're going to do is compile the first expression x, then we're going to append that with compiling the second expression y, and then we're going to append a single add operation on the end, which will actually add the result of the two compilations. And then finally, we remember, and it's very easy to forget, we copy down the stack S here. So now we can think, well, what are we actually going to do? Well, we can look inside the brackets here, and we see that we have a repeated use of append. So probably we're going to need to decide whether we bracket this one way or the other in order to make progress with our proof. And it turns out this time around, the idea is that you should bracket it to the right, and that will turn out to be the right thing to do. So we're going to use the fact that append is associative, so it doesn't matter which way around you bracket it, but this time around, I'm going to bracket it to the right. So I'm going to have compilation of x plus plus, and then in brackets, compile y, and then plus plus, and then add, and close the brackets, and I've got S. So now we can look at this term here and think, what can we do? Well, we think, well, we're doing an inductive proof. Could we apply either of our two induction hypotheses? And unfortunately, if you look at the details, neither of the induction hypotheses are applicable at this point. So we think, well, what can we actually do? Well, we could try working backwards, but actually, if you try it, that's actually not going to help in this case. The trick here is that you actually need a small lemma, okay, a small helper theorem. And the trick, or the observation, is what we're doing here is we're executing the result of appending two pieces of code together. Okay, so we can have a little lemma which tells us what happens if you try and execute two pieces of code appended together. So let me move on to the next page, and we'll just formulate a simple distributivity lemma. So this is always a hard word to spell for me. So distributivity, hopefully that's right. So we've got a distributivity lemma. And the lemma itself is very simple and very intuitive. It simply says, if you execute the result of two pieces of code appended together, C and D, in the context of a given stack S, then it tells you what the result is going to be. And this is very intuitive. If I want to execute one piece of code followed by another piece of code, all I need to do is execute the first piece of code. That will give me a new stack, and then I use that stack to execute the second piece of code. So we can write this down formally. It's very straightforward. All we're going to do is this. Okay, so let me again explain this in words. If I want to execute the result of appending two pieces of code using an initial stack S, all I'm going to do is execute the first piece of code, C, using that stack. That will give me a new stack, and then I can use that to execute the second piece of code. So this is a simple distributivity lemma. And I'm not going to give you the proof here, but you can actually prove this as well by induction on the C parameter. But there's a little wrinkle in the proof, and we'll come back to this later. And the proof actually assumes or requires that the stack is never going to underflow. Because depending on what kind of code you pass in here for the parameters C and D, they may have particular stack demands, and this stack S has to have sufficient number of numbers on the stack to actually accommodate that code. So you can prove this by induction on C, but it does require that the stack never underflows. So you can look at the book if you want to see the details of that proof. So we can go back to our calculation now and look at what we actually have. So we have exactly the form that we need to apply the distributivity lemma. We're executing the result of appending two pieces of code in a given stack. So we know using the lemma now, what we can do is that's going to be the same as executing the second piece of code, which is comp y plus plus add, in the stack that results from executing the first piece of code. So we've got execute comp x and then s. Okay, so make sure you understand exactly what's going on here. This is the second piece of code. So we execute the second piece of code in the stack that results from executing the first piece of code, which is compx. So we're just applying the lemma here. So why was this actually a good thing to do? Well, it was a good thing to do because now we can apply the induction hypotheses for x. If you look at this expression here in yellow, this is exactly the form of the left-hand side of our compiler correctness theorem, where the expression E is actually the expression X. So by induction, we're allowed to assume that executing the result of compiling X in any old stack S is the same as evaluating X in the same stack. So if we apply, at this point, our induction hypotheses to the part in yellow, then let me just copy everything down. What we're going to get is we get compile of y plus plus add, close the brackets, and then what we get in brackets here by induction is this part is now the same as evaluating x and putting it on top of the stack S. Okay, so we've applied the induction hypotheses for x. So now we can look again at this whole expression and think, well, what can we actually do? So we would like to be applying our induction hypotheses for y at this point, but it doesn't quite work at this point. But we see we can apply our distributivity result again. Because what we're doing here is we're executing two pieces of code appended together using a given stack. So we apply our distributivity property once again, and this tells us that this is the same as executing the second piece of code, which is just the add. So if we execute, if we execute the second piece of code, which is the add operation, sitting on a little list on its own, and then what we're going to do is execute the first piece of code, which is comp y, in the context of the given stack, which is eval of x colon s. So again, just to emphasize what we've done, we've got two pieces of code appended together here. So the distributivity lemma tells us that if we execute those two pieces of code, what we do is we execute the first piece of code using the stack, and that will give us a new stack, and then we can use that new stack to execute the second piece of code. So again, just a simple application of the distributivity lemma. So why was this a good thing to do? Well, at this point now, we can now apply the induction hypotheses for y. Because what we have in the yellow here is we're executing the result of compiling y in a given stack. And that's exactly the form of the left-hand side of our compiler correctness equation. So again, this time, we can use the induction hypothesis for y here, and what we will get is we'll get execute, we copy down the addition, and this is going to be, we're going to get eval of y colon eval of x colon s. So all we have done is we have used the induction hypothesis for y, which allows us to replace this part in yellow by this other part in yellow down here. So we're nearly completed the proof now. We just need to kind of wrap things up. So the next thing we can do is we can actually perform the execution of the addition. So remember what add does is it takes two things on the stack. So here we have eval of y and eval of x, and it's going to add them together and put them back on the stack. So if we simply apply the definition of the execution function at this point, so it's very straightforward, all we're going to get is we're going to get eval of x plus eval of y sitting on the stack S. And there's an interesting little technical point here. Note that the arguments come off in the wrong order. We have x here sitting on the top, and then we have y put on top of that. So y is now the top thing on the stack, or the result of evaluating y is the top thing on the stack. But when we do the addition, we actually reverse the order. So this actually doesn't matter for something like addition, which is commutative, but if we had a different source language, maybe which had subtraction or division in it, then you have to make sure to pull things off in the right order. We have done so here. We've made sure to swap the order of the arguments. So to complete the calculation, it's very obvious what we're going to do now. What we have is eval of x and eval of y, and that's exactly the same thing as, to complete the calculation, that's eval of add x, y, given the stack s. And this completes now the inductive calculation because we have shown that this expression or this term here is equal to this term here, which is exactly the form of our correctness equation where E is the addition of two sub-expressions x and y. So this completes now the inductive proof. So what I'd like to do now is reflect for a moment on the proof which we have just done. And in particular, I'd like to think about how many steps are actually involved in this compiler correctness proof. So it turns out if you add up the steps involved in the compiler correctness proof and also the proof of the distributivity lemma, there are 22 steps in total. And for me, this is a bit unsatisfactory because fundamentally our compiler is a simple two-line program. So it's a bit unsatisfactory that in order to prove that this two-line program is correct, we actually need a 22-line proof. So the question we're going to be thinking about for the rest of today's class is how could we simplify this proof? And the trick is that we're going to learn, or we're going to use what we've learned about in the last two classes, which is the idea of rewriting recursive functions in accumulator style to avoid the use of append. And what we'll see is if we rewrite our compiler in accumulator style, the proof is going to become much simpler. So let's start now to rewrite our compiler. So we're going to rewrite our compilation function, comp. And it's going to have the same type as previously at the top level. It's going to take an expression as input, and then it's going to compile it down to some code. But this time around, we're not going to define the compilation function directly using recursion itself. We're going to define it indirectly in terms of a helper function called comp prime, which is going to do a bit of compiling and a bit of appending, just like we had with the fast version of reverse and the fast version of tree flattening in the last two classes. So comp prime is going to take an expression to compile, which in this case will be E, and then it's going to take a list comprising some code to append on the end. This is our accumulating parameter, and initially this accumulating parameter is going to be empty. So what we could do at this point is formulate an equational specification for what comp prime is supposed to do. This is very straightforward. It just compiles the expression and then appends the list on afterwards. But I'm actually not going to do the calculation here for you. I'm not going to apply constructive induction. I'm just going to give you the resulting definition for the comp prime function because it's actually very similar to the flatten function which we did in the last lecture. But again, it's a really good exercise. I suggest formulating the equational specification for comp prime using constructive induction to then calculate the definition which I'm going to give you here. So there's the type for comp prime. It takes an expression, to compile, some code to append afterwards, and then it gives you the resulting code at the end here. So the definition is actually very similar to the flattening function for trees, which we had in the last class. So if you're compiling a value n, and then you want to put the code C on afterwards, all you're going to do is emit a push operation, and then put the code C on at the end. So again, we're compiling the value n. That just translates down to pushing, and then we want to append the code C on at the end, and this time around we can just use the colon operator to put the code C on the end of the push. So no use of append. Then in the recursive case, this follows the same kind of pattern. as we had with the flatten function on trees in the last class. So if we want to compile an addition of two sub-expressions x and y, and then we want to append the code C on at the end, all we're going to do is compile the expression x, then we're going to compile the expression y, and then we're going to omit an add operation, and then we're going to have the code C on the end. And again, note that this definition does not use the append operator at all. And again, maybe the part in yellow is kind of not immediately obvious that this is the correct definition, and you may need to think about why this is actually the correct definition. But of course, you could just calculate this using constructive induction like we have been learning about in the last two classes. So just to summarize here, what we have done is we've defined a new version of the compilation function in terms of a helper function which uses the idea of having an accumulating parameter to avoid the use of append. Now that we have defined our new compiler which uses an accumulating parameter, we can return to the main topic of today's class, which is the issue of compiler correctness. And in particular, we can ask ourselves, what does it mean for the new compiler which uses an accumulating parameter to be correct? So the way I'm going to come at this is we'll write down our original compiler correctness equation, which we've just done the proof for, and then we'll think, how can we generalize this to our new compiler which uses an accumulating parameter? So here's what we had previously. If you execute the result of compiling the expression E using a given stack S, that should be the same as evaluating the expression E and putting it on top of the stack. So if you compile an expression to get some code, execute that code using an initial stack, you'll get the same stack back, but the value of the expression on top of the stack. So this is the result which we just proved. But unfortunately, the proof took 22 steps, including the proof of a distributivity lemma. So what we'd like to do now is take this compiler correctness result and formulate an equivalent version or an alternative version where we don't use the comp function here, but we use the helper function comp prime. And remember, comp prime takes two parameters, an expression E to compile, but also some code C which you want to append afterwards. So let's get rid of this compiler correctness result and formulate an alternative version for the helper function comp prime. So this is going to be very straightforward. So what I'll do first of all is I'll modify the left hand side, and this is very easy. All I'm going to do is replace the comp function by comp prime. We take the same expression E as a parameter, but now we take the second parameter, which is some additional code that we want to append to the result of compiling the expression E. Because remember, comp prime does a bit of compilation. It compiles the expression E, and it does a bit of appending. It's going to append the code C on the end. So we've modified the left-hand side to use comp prime rather than comp, and that's very straightforward. And then we think, well, what do we need to do on the right-hand side? Well, this is actually also going to be very straightforward. What I'm going to do is I'm going to evaluate the expression E as previously and put it on top of the stack S. But I need to remember that I still need to afterwards evaluate or execute this code C. So what I'm going to do on the right-hand side is I'm going to execute the remaining code C in that particular stack. So the only change on the right hand side is this part is exactly the same as what we had before. You evaluate the expression E and you put it on top of the stack S. But now on the right hand side we must take account of the fact that we have this additional code C which is appended to the result of compiling E. We must do something with that on the right hand side. So all we do is we execute that remaining code in the stack that results from evaluating the expression E and putting it on top of the stack S. And it's actually very easy to show that this is a straightforward generalization of our original compiler correctness result. In particular, if you take the code C to be empty and you just check through a couple of little calculations, you'll find that the left-hand side reduces to exactly what we had originally, and the right-hand side reduces to what we had originally as well. So this is a straight generalization of our original compiler correctness result, but for the case of the compilation function comp prime. And in the case when C is empty, it reduces to our original compiler correctness result. So this is what we have to try and prove now. So let me, as we usually do, write the main thing in a little red box. So what we want to do now is prove that this equation is true by induction on the expression E. So as usual, we're going to start the proof off by doing the base case. So we can think, what do we actually need to prove in the base case? Well, this is when the expression E is simply a value n. So what we need to show is that the left-hand side is the same as the right-hand side in the case when the expression E is simply a value n. So this is going to be very straightforward to do. Let's do the calculation. So we'll start off with the left-hand side. We're executing the result of compile prime of the value n followed by the code C given the initial stack S. And it's going to turn out to be just a simple three-step calculation this time around. So what do? Well, we could apply the definition of the new compilation function. We know how to compile prime a value. All we're going to do is, let me copy down the exec first. So when we compile a value, we just push that value, and then we follow on with the code C, and then we can just copy down the stack S here. So all I've done here is I've expanded the definition of the compilation function, which we just defined, and we get push n followed by C. Then in the next step, it's clear what we're going to do. We're going to execute the result of a push. So we could just apply the definition of the execute function, and this will also be very straightforward. All we will do is execute the remaining code C in the stack that results from pushing the value n onto the top of the stack S. So we have this push instruction or push operation here. That's going to have the effect of putting the value n onto the top of the stack S, and then we need to continue afterwards by executing the remaining code C. And then in the final step, to reach what we want, all we're going to do is unapply the definition of the evaluation function, and we're going to expand the n here into eval of val of n, and that will give us exactly the expression or term that we want. So we have eval of val of n followed by S. So again, all I've done in the final step is I've unapplied the definition of the evaluation function, so I've expanded n to be eval of val of n. So what we have achieved in the base case is we've shown that this term is equal to this term, which is exactly the form of our compiler correctness equation when E is the value n. So we have now completed the proof of the base case. Now we can move on to the inductive case. And this is going to proceed in precisely the same way as the base case. We're going to start with the left-hand side of the compiler correctness equation, and then we're going to try and show it's equal to the right-hand side in the case when the expression is actually an addition of two sub-expressions x and y. So we can start by writing down the left-hand side. So we're executing the result of compiling prime, and then we have an addition of two sub-expressions x and y followed by some code C in the context of an initial stack S. So then we can look at this term and think, well, what can we do with it? And the first thing we can do is simply apply the definition of our new compilation function comp prime, because we know how to compile an addition. We just defined that. So if I expand out the definition of compile prime for an addition, what I'm going to get is execute the result of comp prime of x, and then I'm going to have comp prime of y, and then I'm going to perform an addition. I've got the code C sitting on the end, 3 close brackets, hopefully that's correct, and then I have the stack S sitting here as well. So then you can look at a term like this one and think, well, this looks fairly complicated. What could I actually do with this? And actually, if you stare at this, you can see that you can already apply the induction hypothesis for x. Because what we have is we're executing the result of compiling prime x with some additional code here in the context of a given stack. And that's exactly the form of the left-hand side of the compiler correctness equation when the expression E is actually x. So we have got execute the result of compiling prime, the expression x, then we've got some code C following on afterwards in an initial stack S. So by induction, we're allowed to assume that that's the same as this, in the case when the expression E is actually the expression x. So what I can do then is take this whole expression, apply the induction hypothesis for x, and if I carefully perform the appropriate substitutions, I'll get comp prime y of add followed by C, and then on the stack I'm going to get eval of x followed by S. So again, there's quite a lot of moving parts here. You maybe kind of need to track this through yourself, but all I have done in moving from here to here is applied the induction hypothesis for the argument expression x. So now I can look at this expression, and it hasn't really got any simpler. It's still quite a jumble of symbols, but actually already with no further calculation, I can already apply the induction hypothesis for y. Because what I have now is I'm executing the result of compiling prime y, then I've got some additional code, and this is my initial stack here. So if I simply track through the appropriate instantiations and I apply the induction hypothesis for y, what I'm going to get is executing the result of the additional code, add followed by C. Then I'm going to put eval y on top of the previous stack. So I'll get eval y, eval x, colon s. And again, you may need to track through this yourself, kind of pausing the video and maybe taking a piece of paper. In moving from here to here, all I have done is applied the induction hypothesis for the argument expression y. So the rest of the proof is actually very straightforward. Now we're executing the result of performing an addition on a stack which has 2 values at least on top of it, eval of y and eval of x. So we know how to perform an addition. That's just the definition of the execution function. So what we'll get then is execute the remaining code C in the stack, which is obtained by evaluating x and evaluating y and adding those two things together and then putting that on top of the stack. So all we've done is we've taken the top 2 things on the stack and added them together and put them on top of the stack. But we need to remember, of course, we have this additional code C, so we need to remember that we still need to execute that as well. And that's what the execution function does for us. And then in the final step, it's the same as in the base case. We can unapply the definition of the evaluation function. The part in yellow here, if we unapply the definition of the evaluation function, this is going to be simply the same thing as executing C in eval of add x, y, followed by s. Okay, so if I applied the definition of the eval function here, I would get eval of x plus eval of y. So in going in the reverse direction and going from here to here, I'm simply unapplying the definition of the eval function. So if you were to write the hint down, that's what you would be writing down. So now what we have done is we have completed the inductive case and the base case for the proof of our new generalized compiler correctness theorem. So I think it's worth spending a couple of minutes now kind of reflecting on what we have done, and in particular thinking about what kind of benefits we have got from reformulating our compiler and reformulating our compiler correctness theorem to use an accumulating parameter. And for me, there are 4 benefits which we have gained. So the first one is that our original proof of compiler correctness, which also involved having a distributivity lemma, which we need to prove, that took 22 steps in total. If you add up the number of steps in our new proof, there was 3 in the base case, 5 in the inductive case, so we have reduced the overall size of the proof to 8 steps. And for me, this is a completely reasonable sized proof for a 2-line program, whereas 22 lines or 22 steps seems to be a bit much for proving that a 2-line program or a 2-line compiler is actually correct. So that's our first benefit. Our second benefit is that our original proof actually required 2 lemmas or 2 auxiliary results. It depended on the associativity of append, which you need to prove, and it depended on the distributivity of the execution function, which we also needed to prove. If you look back to our previous proof, or our new proof rather, it doesn't use any lemmas at all. Okay, so our new proof didn't depend on any lemmas at all. So we've reduced the lemmas from 2 to 0, which is another benefit. The third benefit is we have eliminated the use of append. So we saw in the previous 2 classes that when you use append, it can result in your recursive programs being inefficient. We have eliminated the use of append, so it has vanished. So not only has this simplified our inductive proof and avoided using any lemmas, but it's also made our compiler more efficient. And finally, in the original compiler correctness proof, in the proof of the distributivity lemma, there was a stack underflow assumption or a stack underflow side condition. The lemma was only valid if the stack contains sufficient elements. That was a bit of a wrinkle. This has disappeared completely. We didn't need the distributivity lemma anymore. The stack underflow issue goes away, so this has vanished. Okay, so for me, this is 4 benefits of what we have done. We have reduced the size of the proof. We've made it simpler. We've eliminated completely the need for any lemmas. We've got rid of the append operator, which makes our compiler more efficient. And we have got rid of the stack underflow side condition on the distributivity lemma. So we have 4 nice benefits of what we have done. So to wrap things up now, I've got one final concluding slide. And what I've put onto this slide is the final sentence from the book chapter, which we've been working through on reasoning about programs. And what it says is that mathematics is an excellent tool for guiding the development of efficient programs with simple proofs. And that's really what I've been trying to illustrate to you in the second half of the course using some simple examples. So this is now the end of the course. I hope you've enjoyed learning about some more advanced functional programming with me this year, using this kind of unusual medium of YouTube videos. It's been real fun for me to make these videos. And I also hope it's not going to be the end of your Haskell journey. I hope that you're going to kind of take the ideas which I've been teaching you forward and actually learn more about Haskell in your own time as well.